Alright, welcome back to the SciMax channel on electronic lab notebooks. Today I'm going to show you a little example of controlling a remote instrument. And the remote instrument is actually in Salt Lake City, and I'm here in Pittsburgh, Pennsylvania. This is a picture of that instrument. I'll show you the references and details of it. But the gist of it is there is an RGB red, green, blue LED, and you can set the different RG and B levels, and then up here there's a light sensor with 8 channels that measures the intensity at 8 different wavelengths. And this work is done by Taylor Sparks and Baird, who decided they wanted to have kind of a minimal example of a self-driving lab, so they built this little instrument as a way of testing ideas on self-driving labs. And this is what I'm interested in exploring today. So they have a YouTube video. You can check it out. You'll find this in the source later. And they have a YouTube video on how they make the instrument. There's a GitHub repo, and there's an example of a Google Colab, which is a Jupyter notebook in the cloud that you can use to run their instrument. And I thought that was pretty interesting, but I wanted to explore using SciMax and Emacs to run that instead. And since this is Google Colab just uses something like a Jupyter kernel, we can also use a Jupyter kernel here in SciMax to run it. Okay, so the gist of this experiment is that you send three integers for the red, the green, and the blue settings of that LED, and you get 8 measurements back, 1 for each channel of the light sensor. And I wanted to do a simpler experiment than they demonstrated. They show, some active learning, machine learning types of demos. I wanted to do something even simpler and do a few experiments. We'll do them manually to figure out, how it works, and then later we might build on this. So I want to find the RGB settings that result in the 470 channel measurement having a value of 10,000. They do a little more sophisticated, finding RGB, like all 3 of them in an optimization, but I thought we would start, again, as simple as we can to learn what happens in a self-driving lab. All right, so I've already installed the self-driving lab demo. And this is the code that is kind of minimal code to get an experiment. You have to define an ID. We have to get a client with this function here. I pulled this all from the Colab notebook. And then down here we call this function to observe the sensor data. You give it your RGB values, and just delete these results. And we'll run this again. And this will take, it takes anywhere from 5 to 12 seconds usually before it will put some result in. So that's like an annoying amount of time to make mistakes on. You certainly don't want to run this 100 or 1,000 times to figure it out. But here I ran 0, 0, 100, so the blue value was set to 100. And if we look down here at this, we get some JSON output. There's some timestamp that's helpful. We have CH470. This has a value of about 20,000. And then the other ones, this is 470 nanometers. That's pretty close to blue. The other ones are much, much lower, order 1,000. There is also a background, so we could, I'm not going to do it today, we could use this background to subtract off some values. So now the goal would be, how do I get CH470 to be 10,000, not 20,074? So we need to do a couple of experiments to map out, how does CH470 depend on this B value. And I think we'll try integrating Hashcash in this. And so for us to do that, we need a function. And I'm going to make a function that returns results down here. So let's get started. Def, let's just call it get results, and we'll have 3 arguments, R, G, and B. And then we can just copy this and return that, that result. So this is going to return the JSON data. And one thing to think about now is what happens if I want to run an RGB multiple times. Since this is an experiment, let's just try running this for a few times. Get results 0, 0, 100. And this is going to return a dictionary, so I'm going to just index out CH470. And let's run it manually a few times and see what happens. Now, if I was doing this with Hashcache, it would return the initial result every single time for that particular RGB values. So here I got 20,053. The last time we got 20,074. So they're not exactly the same. There's a little bit of noise in the measurement. That's because it's a real experiment. And so we can't directly Hashcache this, or we will always get the first value, and we need a way to differentiate those. And so what I'll do here is just add label equals none. And this will give me an optional 4th argument that I could use if I wanted to run this many, many times. All I have to do is change the label. Okay, so now let me import PyCache. And then I can decorate this. And we'll run this one again. So let's see, I'll count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that took about 11 seconds to run. But now the second time I run this, it instantaneously returns that value. It does not run another experiment. And so I would have to say, you know, label equals 1 to get a new value that's also going to take about 10 or 11 seconds. All right, but then for our future analysis, I will be able to run these pretty conveniently. Okay, let's do our first set of experiments. Let's say B is going to be, let's do 0, 50, 100, 150. I guess we already know that 100 gives us 20,000. So let's do 0, 25, 50, and 75. And I'm going to plot this. And then let's do a list comprehension. And this will run our experiment for each value of B, 1, 2, 3, 4, 5. This is probably going to take about a minute to run. And you know, I'm going to do this with async so that I can keep doing stuff while it runs. And let's add for TQDM. And I'm going to make this be The reason I changed this is, and I'm going to make this be TQDM. This is going to make it be a little bit obvious, I hope, when this runs. Oh, what did I do here? And we should see down here a counter. So it'll update about every 10 or 11 seconds and show me that something's happening. That way I don't have to wonder, like, is it hung? Is it doing something? Etc. Okay, so we'll look at next. Let's look at just CH470 when that's done, and we'll get an idea of what's happening. All right, so we get somewhere around 50 is going to be close to that. Let's make a plot. All right, so it's pretty linear, but it's not totally linear. So at least in this range, somewhere around here is pretty linear. And so what I'm going to do to figure out how to get to 10,000 is not fit a line, because the line's going to get skewed by this value down here. Let's do an interpolator instead. And instead of interpolating CH470 versus B, I'm going to do it in the opposite way. CH470 comma B, and then I can just evaluate I of 10,000, and that tells me that I really want a value of 52.38, and we can only send integers, and so we'll round this down to 52. All right, and now let's just have another loop. We're going to run it. Let's just run it 5 times. And remember, I have to differentiate each one of these because we have cached it. And I'll just pull out this particular one, and I'm going to put TQDM again here. It may not be the right thing to do this time, but let's see what comes out. Get result is not defined. Get results. All right. Looks like we got 9918. So we're close to 10,000, but not exactly 10,000. It's possible we need to round up. It's also possible that we can't get 10,000. And this, seeing both of these here is why I wasn't totally sure this is the right thing to do with async. That's a feature really of this notebook. So instead of doing this, let me just make this 53, and this one is probably going to be a little bit above 10,000. So it looks like it might not actually be possible to get exactly 10,000 since we're limited to integer inputs. And so we'll either have to be a little bit under or a little bit over. We could do some more statistical analysis of these. In fact, maybe I'll go ahead and do that. Now that these are cached, we simply run this again. Let's see. So I use a list comprehension to just rerun and extract those results. We get 99.23 is the mean, standard deviation of 7. So there's no question this doesn't include 10,000. And then I can do the same thing for this other result. Let's say it's R53. And this one also has a quite low standard deviation compared to this, and undeniably does not contain 10,000 in this case. So that's actually the end of this small experiment today. We did a set of 5 measurements to map the dependency of CH470 on B, and based on that, we used an interpolating function because this is not totally linear. You might be able to fit a parabola or something like that, but I just chose to use an interpolator. The interpolator tells us we need a fractional intensity, but we are only able to send a integer to this device. I'm pretty sure if we try to send it a non-integer that we'll get an error. Let's double check. That's because there's a discrete, it takes discrete values from probably 0 to like 65,000 something. And the discrete values are based on discretization of a 16-bit output. So let's see if it gives us anything. Yeah, so here it says that 52 does not equal 52.2, and that's an assertion inside the code to make sure that we only use integers. So that's the root of that particular issue. And it just says that it will not be possible to get exactly 10,000. We'll have to get something that's close. And it looks like this one is only about 80 away. And this one is over 100 away. So this one that's slightly under is lower in that sense. This is an integer programming kind of problem that results in that particular result. Okay, I didn't look into how the communication with this device actually works. I assume it's behind a web server and there's a REST API buried inside the self-driving lab demo. And so this is sort of like just communicating with an instrument via a REST API. But we do it through Python, where all the communication is abstracted away in this observed sensor data. And you could do all kinds of things now where you could wrap this function inside an optimization idea. We could probably do that. And maybe you could get to that in a small number of steps. We only took 5 steps here. Since it's so linear, especially if you could assume linearity in the region, you might be able to do an active learning step. But I'll save that for another day. It's not really something that needs to be in the electronic notebook measurement today. So shout out to these authors for creating this and making it available. I think it's pretty cool. We could even connect to it and make some measurements and try out some ideas. And I've ordered a couple of these, so hopefully I'll have a local one that doesn't take 10 seconds per measurement, and then we can explore active learning strategies more quickly that don't take 10 seconds per evaluation. All right, that's it for today. Thanks for listening.